This is joint work with Florian, and this is a paper about fair division with an underlying theme about richness in discrete models. So let me explain what I mean by that. Um, so a lot of fair division literature involves a model that's not discrete at all. We have a perfectly divisible cake or pizza that we'd like to cut up and allocate in a way that's fair. And then another strand of the literature involves models that are completely discrete. So have in mind a finite collection of indivisible objects like a gem box, and there getting exact fairness may be too much to ask. If, for example, we all think the diamond ring is more valuable than the rest of the box, we're in trouble. So typically the goal is to go for some notion of approximate fairness. And what we're going to be interested in this paper is really going for exact fairness, even in a completely discrete model. So before I tell you more about what I do, let me tell you what I don't do. In practice, one way you can get exact fairness with a gem box is you can sell it, and then you can divide up the money evenly, right? Or you could draw a participant's name out of a hat uniformly at random and give them the whole box. And so what these solutions involve is adding something divisible to the model, either money or probabilities. And we're not going to do that. We're really going to be working with a completely discrete model here. Right. So in particular, we revisit this recent taking turns model of Mackenzie and Komornik, where the idea is, let's say there's a vacation house, and this is going to be divided up among participants, not by space, by rooms and floors, but by time. But the catch is time is not infinitely divisible here. There's some basic units that can't be cut up further. They're called time slots. Sometimes I'll call them dates. So you can imagine we have the calendar, and this is really a stylized model here. All the participants are going to live forever, right? So we have one date for each natural number, on and on forever. The idea is with so many indivisible objects, can we have enough richness in the model to guarantee that there exist exactly fair allocations? And what Mackenzie and Komornik showed is that if there are three agents, that's true. If there are three participants and everybody is patient enough, there are exactly fair allocations. And so what we do in this paper is we consider the general case where there might be any number of agents. So let me already start to be more precise about what I mean here. So in the model, we have a finite set of agents. These are the participants, if you like, who are going to be sharing this vacation house. And we have this infinite collection of time slots, one for each natural number. So if you like, 1 is today, 2 is tomorrow, and so on. Now, each agent is going to consume a collection of time slots, which we refer to as a schedule. Right. So this set here is each agent's consumption space. And in agents' ranking of schedules, we're going to represent using a countably additive probability measure. Right. So this is pretty standard in fair division. We're going to normalize the value of consuming the full calendar to be 1. And then we have this additivity, right? If there's two disjoint schedules, then the value of their union is the sum of their values. Right. There's no complementarity for certain dates. So this is how I'll illustrate the model on the slides, right? The leftmost date is the earliest one, if you like, that's today. And moving to the right, we have later and later dates. Right? And I've highlighted in green a collection of dates to represent a schedule intended for the green agent, who's the only agent on the slide right now. Right. And a utility function for this agent, I'm just going to say the same thing a different way, he assigns a value between 0 and 1 to each date, and he does so in a manner that they sum up to 1. Right? And that represents preferences over schedules because the value assigned to a schedule is just the sum of the values assigned to its dates. Now, for this talk, I think it's going to make things a lot more clear. Let's assume that this is monotonic in the sense that later and later dates get worse and worse, or at least not better. We relax this for some, but not all of our results in the paper, but for the talk, let's just carry this throughout. And what we'd like to do with these agents and their preferences is allocate the dates, right? So we partition the calendar into schedules, one for each agent. And so the way I illustrate that here, the blue dates are for the blue agent and so on. Okay. So the goal is to select an allocation that is fair. And we articulate fairness in two pretty standard ways, right? The stronger the allocation is envy-free if no agent values another schedule more highly than his own, right? And the weaker notion, this is implied by no envy, but it's weaker, is that each agent values his own schedule to be worth at least 1 over n. Okay. And I want to emphasize this is a completely discrete model that we're talking about here, but we're going to be going for these fairness notions exactly. I'm not going to have any sort of approximate fairness in this talk. So if you think about this problem for a minute, you realize this is completely hopeless if everybody's really impatient, right? For example, if all of us assign value 1 to today, then the fact that we have this infinitely many other dates is useless, right? We essentially have one indivisible good and we can't do anything about that. So the way we inject richness into this discrete model is to require the agents to be patient. The way we formalize patient is with this notion that builds on an idea from Kakaya from over a century ago. It's a heavy tails condition. And let me just skip ahead to the picture here. What it requires is that for each and every date in the calendar, right? If you compare that date in isolation to the schedule of all future dates, all later dates, the future is worth at least k times as much as the present. Okay. And that's true in this slide. I've selected arbitrarily this red date t, but that's true for each and every date. Right. So not just this given blue tail, but all tails are heavy relative to the present. And as you increase this parameter k, you get more and more patience. Okay. Now, this observation that this is a hopeless exercise without enough patience, it's not too hard to provide this necessary amount of patience. If I'm not n minus 1 Kakaya, I might assign more than 1 over n to today. If we all do that and we have identical preferences, we can't make something proportional. So n minus 1 is kind of this easy, necessary amount of patience to have a chance here. And it turns out from the literature that this necessary amount of patience is also sufficient in a couple of interesting cases. So notably, if all of the agents have identical preferences, this necessary amount is also sufficient for no envy. Right. Actually, for the special case of geometric preferences, this is essentially a classic result for repeated games that goes back to Soren, Pudenberg, and Maskin. Now, when you have two agents who may have different preferences, the necessary amount is still sufficient for no envy. And when you have three agents, the necessary amount is still sufficient, but now just for proportionality. Right. And beyond this, we don't know, right, from the literature. And so what we do in this paper is to consider an arbitrary number of agents. We relax a bit about getting this necessary and sufficient level. We allow there to be some gap and allow some extra patient that we're not sure if it's necessary or not to try to get a sufficient amount. So that's what we do. And the sufficient amount lets us articulate the idea that if everybody is patient enough, there are fair allocations to be found. Okay. So what I'm going to do to structure the rest of the talk is essentially, I'm going to take you through a key lemma and some of the ideas that give you some intuition for how to play around with this model, and then explain how that key lemma gives us our proportionality result and our no envy result. So first, a new concept. Take an infinite schedule. It could be the full calendar or maybe just the even dates or maybe something else. Take any infinite schedule. This schedule we'll say is k divisible to an agent, let's say maybe to me, right? If essentially it's this k Kakaya heavy tails condition again. If when I throw out all the other dates, so I pretend these are all the dates, I think that for each date, the future is at least k times worth the present, right? And that's something that's subjective for a given infinite schedule. I might think it's k divisible and you might not. Okay. Why this is useful it turns out if I give you a schedule that you think is k divisible, and I give you a target value v, and I ask you to cut this schedule so that one of the pieces is worth exactly v, you're going to be able to do that in a very simple way, right? Using just a basic greedy algorithm. So if you start at the beginning of the schedule that I gave you, and you add a date to the basket, unless you think that would make the basket worth too much, and then you skip it, this is going to work. And the reason is, if you skip a date, well, because you consider this schedule to be divisible, there's always enough later, right? So in your basket, there's never too much, but if you have to skip something, there's always enough. And in the limit, the value of this basket will be precisely the target value. Moreover, suppose you cut that piece that's worth v to you and you eat it, and now we look at what's left, right? For each date that remains, let's say this one, you originally thought that the future had k todays left. Now you skipped this because you thought that would be too much for your basket, which means you took at most one today from the future while performing the greedy algorithm. So now you think that there's at least k minus 1 todays remaining. Good. So when you do the greedy algorithm, right, what remains, you think for each remaining date, there's at least k minus 1 todays. That's true for each and every one of these dates. What remains is k minus 1 divisible to you. So if you think an event is k divisible, you can make k cuts using the greedy algorithm, right? Now, the trouble here is what we might want to do is have some interactive cuts, right? Maybe I start with the calendar and I make a cut, and then from one of those two pieces, Florian makes a cut, and then from one of those pieces, I make a cut. And this is a problem for the greedy algorithm here, because when I use the greedy algorithm, I guarantee that what remains is k minus 1 divisible to me, but not necessarily to Florian. So the challenge is to maintain some consensus that what remains after a cut is divisible. And this is exactly what we're going to use the extra fairness to accomplish, the extra patience to accomplish. So the basic idea, let's suppose we start from an event, maybe it's the calendar of everything, that everybody agrees is k divisible. And now, not necessarily from the start of that event, take an arbitrary date within that schedule. I picked the blue one, and let's look at that date and those that follow. Okay. Now, the idea here is to partition the dates we're looking at into cycles. We call them cycles, right? So if it's a C cycle, that means every C dates, right? You can think of these as residue classes for modular arithmetic, right? Is basically what's in the picture. So left to right here still means earlier to later. I've just arranged them so that they're partitioned into these rows. Okay. So everyone agrees that there are at least, if the blue date represents a today, there are at least k todays in the green box. So if we cut out the starts to the other cycles, that's at most c minus 1 todays by monotonicity. They're all later than the blue date, so they can't be as good, right? So if we cut that out, there are at least k minus c minus 1 todays in this smaller green box. Now, the top row of this, if you take a look at this green box, row by row, each row dominates the row below it in terms of earliness. So by monotonicity, as you go up the rows, they get better. And this is the top row. So it's worth at least 1 over c of what's in the green box. Now, if that top blue row here is worth this amount, right? Then so are all of these blue rows, right? Because the second row dominates the third, which dominates the fourth, which dominates the one that we started with, which was at least this much, right? So everybody agrees that all of these blue rows are worth that much. And because that's true for any arbitrary blue date that we start with, right, that means that each of these boxes is actually divisible, right? If we followed along the top row, there's enough value in what follows for this date, and then we just repeat the argument for the future dates. So finally, this is now the key lemma and the stopping point. any subset of what's on the screen that contains an intact row will be divisible, right? For example, if we have completely contain this third row, and then we add something extra, right, this state, for this state to have enough value in what follows, it would have been enough to follow along its own row, and we have something better than that in what follows. So at a high level, right, what this is saying is if we partition into a fixed amount of cycles, right, C cycles here, and then we jack up this level K, we can build potentially an arbitrary consensus that any one of these rows has an arbitrary level of divisibility. Okay, so that's essentially the key technique here. So to explain the proportionality result, what I'm first going to show you is the three-agent technique from Mackenzie and Komornik, and then why it doesn't generalize and how the key lemma allows us to do that. So again, the Mackenzie-Komornik works for this necessary and sufficient level of patience, but just for three agents, right? And the idea is that these three agents are going to collectively construct and assign one schedule, and then that guy will leave, and then the two remaining agents will do the same thing again. And then the last guy will get the leftovers. And it's a simple process. They're going to go through the dates in order, and like with the greedy algorithm, if somebody thinks that adding the current date to the basket will make it too valuable, you put a flag in. If nobody puts a flag in, you take the date. If multiple put a flag in, we have some serious objection here, we skip it. And if just one person puts a flag in, this is great, only one person wants it, put the date in there and assign the basket to that guy. Now, we then have the remaining two agents repeat the process. If there's no flags, they take, right? And if there's multiple flags, this is where you have to be careful, because the worry is if we skip a date and then nobody thinks there's enough value in what remains, right? These guys are in trouble. But for three agents, if this date was skipped in the first round and now it's skipped again in the second round, multiple agents placed a flag in the first round, multiple agents placed a flag in the second round. And because there are only three agents, that means at least one agent placed a flag in both rounds. So here it's the red agent. The red agent thought there were two todays in what follows. In the first round, he made sure that no more than one today was taken from what follows. And so he thinks that there's at least one today remaining. Right. And so this is why this procedure works, right? Nobody ever lets somebody leave with a basket they think is worth more than 1 over n. And if while filling any basket we ever have to skip a date, at least one of the remaining agents still has some hope to get up to the 1 over n level, right? There's some other details about this, but I'm going to skip them. Those are the main ideas here. And this is the part that doesn't generalize, right? The idea that in a later round, we might be concerned that if we skip a date, there won't be enough value in what follows. And so what we're going to do is use the key lemma to build consensus that in each and every round, what remains is one divisible. Yep. And it's a very simple idea, right? Basically, we're going to partition the calendar into n-1 cycles. And then in each of the first n-1 rounds, we're going to construct and assign a schedule. The final nth agent will get the leftovers, right? And in the first round, they're going to do the procedure, but only on the top row, right? And then in the second round, they'll take whatever they want from the leftovers of the top row and from the fully intact second row, right? And so each round, what's up for grabs includes, it completely contains an intact row. So there's consensus among the remaining agents that it's divisible. And we chose the number of cycles in such a way so that there's enough value in what remains the whole time. And that's basically the proof technique, right? If you have n agents, and this bound is the one given by the key lemma to ensure that each of these cycles is one divisible, then you have a proportional allocation. Okay. I think I'm running a little low on time, so I'm just going to briefly sketch what we do for no NB here. So if for proportionality, we took this Mackenzie-Komornik procedure and modified it with the key lemma. For no envy, we're going to take the greedy algorithm and modify it with the key lemma. So remember what the greedy algorithm does. I give you a schedule and a target value and ask you to make a cut. And you make an exact cut so that the leftovers you consider still pretty divisible. The alternative, we call it the tripartition algorithm. I'm going to give you the same problem, but now when you make a cut, you're going to think not just the leftovers, but both pieces are still divisible. And moreover, not only you are going to think that, everybody is going to think that. Now, the divisibility is not going to fall by just one, it's going to fall quite a bit, but that's okay for our purposes here, right? So omitting some details, briefly, the idea of what we do is given the value, we're going to ignore the first few dates. We're going to carefully pick correctly a starting date and divide that date and everything that follows into 3 cycles. And then from the middle cycle, we're going to skip everything automatically. From the bottom cycle, we're going to take everything automatically. And it's going to work out that we can top ourselves up to hit exactly V by applying the greedy algorithm to the top row. Okay. And now what's nice here, so you have to trust me because I'm skipping details, that the green will come out to exactly have the target value, but it does. And then you can see both the green and the red events contain a complete row, right? So they maintain some divisibility by consensus for everybody, right? And so what that allows us to do is import a technique from cake division. So in particular, there's this Aziz and Mackenzie protocol for constructing envy-free allocation in a bounded number of cuts, right? And what we do is we exactly import that. We take the calendar as our cake, and we make all of the cuts that Aziz Mackenzie protocol would ask us to using the tripartition algorithm. So the Aziz and Mackenzie procedure requires quite a large number of cuts given the number of agents. When we import it, we require a huge amount of patience to be able to make all of those cuts, and we lose a lot of divisibility with each and every one of them. But it's a finite amount, right? And this is the result, right? Regardless of the number of agents, if we have this extremely high but finite amount of patience, so if everybody is patient enough, there are envy-free allocations. I think I'm out of time, so this slide just summarizes the results, right? We have our necessary amount of patience. Some more than that, we guarantee proportionality. A lot more than that, we guarantee no envy. In the paper, we relax the monotonicity for the first result, but not the second. And the summary is that if everyone's patient enough, there are fair allocations. I list a couple of open questions here, but I think I'm over time, so maybe I should turn it to your questions. And thank you very much.
Thank you. Let's give Andrew a round of applause. If you have questions, feel free to raise your hand or write them in the chat. Maybe I can actually start with one. So if I'm an agent and I have to come up with my valuation function for this infinite time, right? It feels kind of difficult because I have to be monotonic, I have to converge. So I personally would just throw my hands up and just use some geometric factor and that's it. But of course, make the model interesting, it needs to be more personalized. So what kind of considerations, what kind of freedoms do I have to make a valuation function for myself?
So, I mean, this is a great point. If what you wanted to do is say each agent, your preference is just summarized by one number, discount factor, everything I say still applies, right? So we have this big class where we allow all this flexibility to custom tailor your preferences. You know, if some of the dates are weekends, you take that into account, fine. If you just want to be simple and tell me your discount factor, right? And so each agent has a discount factor. That's a special case of this model. And so in that simpler model, right, what we're saying is if everybody's discount factor is high enough, then there are fair allocations.
And is that special case much simpler? Do you need the whole machinery that you've used, or would that be sort of more trivial algorithms that make such allocations?
It's a great question. I don't know of any shortcuts that would provide, because essentially none of the arguments that we make rely on or take advantage of stationarity. When you're using this greedy algorithm to make a cut, what comes out is typically going to be something that looks a little bit messy. The leftovers will be in some way messy. So even after one cut, we're not going to have something that your restricted preferences look stationary over. So it turned out that relaxing that seemed to be for free for the analysis.
I see. Interesting. Thank you. Bill, you had a question. Do you want to raise it?
Can you hear me?
Yes.
Yeah.
Okay, so yeah, just are there any implications? This is a kind of a soft question. Might not make any sense. Are there any implications for participatory budgeting in which you consider future years division of the budget? So you replace a single date by a single division of the projects that are available that date, and achieve fairness, through making up, compensating for getting less on one day, but getting more on another day.
Could you ask the question one more time? I'm trying to think about this.
Well, in participatory budgeting, we have future dates as well as the current date when we're drawing up a budget. So we could achieve fairness potentially by not just looking for fairness on the current year, but on all future years summed. And that sounds a lot like your setup.
I'd have to think more about it. I mean, do you have a particular formalization of that in mind? So there would be some set of projects.
No, it's just that a date gets replaced by that year's what is it called? Menu of options for projects, right? So you're going to make some choices you're going to make some choices that are better for some agents than others. You don't achieve fairness on that date, but you have the next date to make up for it, etc.
So maybe if for each date, instead of picking one agent, we're picking one project, something like this. And the preferences over projects might be, in principle, if the possible projects are pick an agent to win today, and I have value 1 for myself and 0 for everyone else, in principle, there could be something more interesting in a given time period. I haven't thought more about it, but I think that makes sense to me. The basic idea how we get richness with patience is it allows for there to be compromises. I'll take a loss today because everyone else, you can make it up to me later. So I think you could do this, but I'm speculating here.
Mm-hmm.
Thanks. Nishak had a question that I'll read out. Do you think that the Kakeya level needed for NV freeness would be little omega of n, so grow faster than n? Because he's thinking of cake cutting, a proportionality requires n log n queries, the Robertson-Webb model, while NV freeness requires n squared many at least, establishing a separation.
I missed the start of the question. Do I think the Kakeya level exceeds what?
Needed for NV freeness grows faster than n.
I don't know. As far as I know, the Kakeya level needed for NV free could be n-1. The techniques that we have to get the sufficient level require far, far more than that. But I don't have strong intuition that you could or couldn't find an example of economy with no NV free allocation. What I spent a lot of time doing before this paper was really being hyper-focused on this n-1 level and trying to generalize that from 3 agents and beyond. And I don't have strong intuition after trying to do that if the result's true or false.
And it sounded to me like if you have an NV-free cake cutting protocol, you can import it into your model. Or is there something special about Aziz Mackenzie that allows you to do the import?
I would say essentially any protocol you can. I mean, what you're going to want to have as input if you have a cake procedure is if at each step you have a finite partition. right? And maybe everyone's evaluated it. And then you ask someone to take a cell of this partition and cut it in a particular way. And you do this over and over again, which is, in principle, you can technically have things a little bit different than that. In certain models of Robertson Webb, you can take advantage of the unit interval structure. But if you have it in this format where there's a partition, pick a cell, and then from this cell, cut out this value, we can import that.
Okay, thanks.
It's very expensive to do that, but it allows us to understand better, the structure of what are the feasible payoff vectors in, say, a repeated game where the agents have different levels of patience, right? We don't understand that well, but this helps us get at it.
Peter, you had a question?
Yes. Do you hear me?
Yes.
Yes.
Okay, now I have a problem with the starting assumption that the total value for every agent of the infinite process is finite. You would expect that this total diverges to infinity, and that the fairness condition should be expressed in the sense that the fraction each agent collects by some time t of the total converges to equal shares if t grows to infinity. Would that be a reasonable alternative model?
I think so. I mean, this makes sense to me. So in the Mackenzie and Komornik paper, they do think about this sort of, I think they call it eternal approximate fairness. So, for each date t, we've allocated some portion, we've allocated the first t dates, and we want that to be approximately fair all along the way. And depending on what notion of approximate fairness you take, right, because you're not going to have exact fairness when you've allocated the finite number of dates. So you're going to have some sort of approximate fairness that maybe you want each and every step along the way. Depending on your notion of approximate fairness, there's some easy ways to do that. So one thing you could do is just rotate, take turns who gets a date. Right, so we line up, I take a date, I go to the back of the line, and we just continually cycle like this. There's another procedure that guarantees you can have n be free up to any object all along the way, but I believe it's not exactly constructive.
You would expect that if you furthermore assume that each individual item has a bounded value, so in the limit, the contribution of a single item is proportional to 1 over the time, then a simple greedy approach would seem to work. You look at the candidate which is underrepresented at some point, and that candidate gets the next item.
I'd have to think about it more to be able to confirm it, but it sounds like a plausible conjecture to me. When you have identical preferences, this procedure works perfectly. You get everyone exactly 1 over n through this. In my model.
Okay, thanks.